Welcome to Economics 1723 Capital Markets, the fifth lecture module on risk aversion, the insurance premium, and portfolio choice. The roadmap for today is I want to talk first about absolute risk aversion and the insurance premium. The insurance premium is the amount that you would pay to avoid a risk that you want to get away from. And then I'll go on and talk about relative risk aversion, which is relevant for portfolio choice, the next topic in the course. So first of all, absolute risk aversion. I want to refresh your memory from last week. We discussed the fact that risk aversion implies a concave utility function. So here's the picture. We have a utility function that looks like this. It curves over. The definition of concavity is that this curve is always above a straight line drawn between any 2 points on the curve. And remember that we said that if you started with some wealth, it gives you this utility here, U of W0. Suppose you're confronted with a fair gamble that increases your wealth by H or reduces it by H. The utility loss if you lose is this amount, and the utility gain if you win is only this amount, which is smaller, so you will turn down the gamble and stick with your safe wealth. And the property of the function that gives you that is the concavity, or the declining slope, the flattening out, and that corresponds to a negative second derivative. So the next question is, how do we quantify the amount of risk aversion? How do we go from saying that people are risk averse to saying how risk averse are they? So there's two important measures of risk aversion that we use. The first is called absolute risk aversion. We write that A as a function of wealth. It may depend on how wealthy you are. And that is the second derivative of the utility function with the sign flipped. We multiply it by -1, and then we divide by marginal utility, by the first derivative. This division here is to make sure that the result is independent of any units that utility may be measured in. Okay, so it's just a scale factor or a normalization, but fundamentally we say that the more curved the utility function, the more negative the second derivative, then with a sign flip, the more risk averse somebody is. Now risk tolerance, and that's a word that's sometimes used, risk tolerance means the inverse or reciprocal of this, 1 over A of W0. And finally, relative risk aversion multiplies A of W by wealth. Relative risk aversion is just defined to be wealth times absolute risk aversion. Well, where do these things come from? I've given you some motivation, but what makes absolute risk aversion, for example, a meaningful measure? Well, I'm now going to show you a very important result, which is that absolute risk aversion has a relationship to the insurance premium, the amount you would pay to avoid a risk. So let's start by defining that insurance premium. Think about a random variable, call it Z, which has mean 0 and variance sigma squared. Let's define the insurance premium, pi, as the amount that you would be willing to pay to avoid this risk. So what's to be more precise, it's the largest amount that you are willing to pay to avoid it. Well, what's that given by? This equation defines it. We're going to compare the utility that you get of certain wealth, W0, minus the insurance premium. We're going to compare that utility with the expected utility that you get if you don't pay the insurance premium and you do accept the risk. Then you have W0 plus Z. Z is random. You have to take the expectation. This is how well off you are living with the risk. This is how well off you are if you pay the insurance premium. The insurance premium is the number such that you're exactly indifferent. You're willing to pay that much, but you don't gain anything. Obviously, if you could get insurance for less, you would actually benefit. Well, to find an approximate solution for the insurance premium, what we're going to do is parameterize the risk as epsilon z for some small number epsilon that's positive. So we're going to consider, in other words, a small risk and see if we can find an explicit solution for that small risk. Okay, so now we're going to write the insurance premium as a function of epsilon, pi of epsilon, and it's the solution to this equation. Again, just the same as the one above, but parameterizing everything explicitly as depending on the scale of the risk. Now, a first point to notice is that pi of 0 is 0. What does that mean? If epsilon is 0, then the risk is non-existent. So if there's a non-existent risk, you're not going to pay anything for it. Okay, you're not going to pay to get rid of it. All right, now we can approximate the insurance premium using a Taylor approximation around epsilon equals 0. So this is, basic calculus, the idea that any function can be approximated in the neighborhood of some point, in this case 0, as the pi of 0, the value of pi at the reference point, plus the first derivative of pi at that point times the small risk scale factor epsilon, plus the second derivative at the reference point times the squared risk scale epsilon squared divided by 2, and so on. We could continue with higher order terms, which are going to be smaller, and we will neglect them. So we already know that pi of 0 is 0, and I'll show you in a slide or two that the first derivative is 0. So the action is going to come here from the second derivative, and we're going to be able to show that that second derivative is this thing. It's minus the second derivative of utility divided by the first derivative of utility. That's the same as absolute risk aversion, times the expectation of the square of z, the variance of, this is the variance of z, because z, remember, has a 0 mean. Okay? So what that means, if we use this Taylor approximation, we discover that the insurance premium is approximately 1/2 times epsilon squared times sigma squared times A of W, absolute risk aversion. Now, epsilon squared sigma squared is the variance of epsilon z. That's the variance of the risk we face. So basically, the insurance premium is 1/2 the variance of the risk times absolute risk aversion. It depends linearly on variance, and it depends on the coefficient, linearly on the coefficient of absolute risk aversion. So this is a very important result because it relates this abstract measure, the absolute risk aversion coefficient, to something we can observe, which is how much people are willing to pay to get rid of risk. Now, since this is an online lecture module rather than a live lecture, I can inflict the details on you. I'm going to show you first how to derive the approximation, the first order term in the approximation, and then the second order term. So recall that the insurance premium is defined as the solution to this equation. We can differentiate both sides of this equation with respect to epsilon. And on the left, we're going to get we're going to use the chain rule of calculus. We're going to get marginal utility times minus the derivative of pi with respect to epsilon. So that's minus marginal utility times pi prime, this first derivative. And that has to equal the derivative of the right-hand side, which is the expectation of marginal utility times the derivative of this argument with respect to epsilon, which is z. Now, we're going to evaluate this at the point epsilon equals 0. And when we do that, we're going to see that we'll have u prime of w0 here and u prime of w0 here. The epsilon terms drop out because they're 0. And so then we can cancel out the marginal utilities, and we'll just have pi prime of 0 is the mean of z, which is 0. So we've shown that to a first order approximation, the insurance premium is 0. To say anything more, we have to think about the second derivative. So how do we get the second derivative? We're going to differentiate both sides of the equation on the previous page. And now the chain rule of calculus really kicks in. Right? You get all these terms. All of this messy stuff here is just obtained by differentiating both sides of this equation with respect to epsilon one more time. Using the chain rule, you're going to get all of this stuff. Now we're going to evaluate this at epsilon equals 0 and use the fact that the first derivative at 0 is 0. So terms like this, pi prime of epsilon squared, this term is going to drop out because pi prime of 0 is 0. All right, so a whole bunch of stuff is going to drop out. What's going to be left, we're going to have minus u prime pi double prime. That's this term here. Shows up like this. And on the right, we're going to have expected second derivative of utility times z squared. All right, and the other stuff, this term drops out. All right, so now if we rearrange the terms in this equation, we'll get the second derivative pi double prime of 0. The second derivative evaluated at 0 is, as I said before, absolute risk aversion times sigma squared. And now we put together all the ingredients, we'll get the key equation 2, which is the one that says that the insurance premium is proportional to variance and absolute risk aversion. It's 1/2 times variance times absolute risk aversion. All right, so that was the first topic. The second topic for today is relative risk aversion and portfolio choice. So when is relative risk aversion useful? Right? Remember that relative risk aversion is wealth times absolute risk aversion. And to understand where this comes in, think about an example in which risk is multiplicative of wealth. So risk doesn't add or subtract to your wealth, it multiplies it. So let's define epsilon to be equals 1. And z is little z times wealth for some risk little z. So an example would be little z is minus 10% with probability 1/2 or plus 10% with probability 1/2. So you're tossing a coin. If it's tails, you lose 10% of your wealth. If it's heads, you win 10% of your wealth. So you're going to end up with either 90% or 110% of your current wealth. All right, so now in this example, the variance of epsilon z is the variance of this little z times the square of wealth. All right, now applying the previous solution for the insurance premium, the premium you'd pay to avoid this risk is 1/2 times the variance of little z times w0 squared, right? The variance of that substituted in times absolute risk aversion. Now, we can rearrange that by dividing through by wealth. Let's look back here. All right, we're going to divide through by wealth, so we'll get a pi over wealth. And then here we're going to have wealth times absolute risk aversion, which is relative risk aversion. So we have that the insurance premium divided by wealth is 1/2 the variance of this multiplicative risk times the coefficient of relative risk aversion. So what that says is that relative risk aversion measures the share of your wealth you would pay to avoid a multiplicative risk. Now in the example that I just showed you where you either gain 10% or lose 10%, the standard deviation of that is 0.1, 10%, and the variance is the square of that, which is 1/100th. So that says that the share of your wealth you would pay to avoid a multiplicative risk is 1/2 times 1%, 1/100th times relative risk aversion. So as we'll see, relative risk aversion is going to be what matters when we study attitudes towards risk in financial markets, risky asset returns, which are multiplicative. And relative risk aversion has an advantage over absolute risk aversion of being independent of the monetary units for wealth. So it doesn't matter whether we're talking about dollars or cents or euros, relative risk aversion will be independent of that choice of units. All right, so finally, let's do a simple portfolio choice problem using the utility function. So imagine that we have an investor who combines various assets to obtain a return on her complete portfolio of all wealth, which is denoted by RC. And to have a little notation, there's the set of all possible returns you could get given the available assets. That's sort of C squiggle. And the expected utility approach is to say that the investor chooses a portfolio that has the maximum expected utility of wealth times the gross complete portfolio return among all possible returns that are in this set squiggle C of available returns. Now we can simplify this problem by using a local approximation. So to a local approximation, which is more accurate for shorter time horizons, the general objective function in the previous equation 5 can be replaced by this. The objective is the mean return minus 1/2 relative risk aversion times the variance of return. Right? So that's what the investor maximizes. And you can see that it's going to be much easier to work with this equation 6 than it was to work with this thing, equation 5. Now let me note that this formula here is equivalent to equation 6.1 on page 170 of Bodie, Kane and Marcus. The book uses, I think very confusingly, the letter A to denote relative risk aversion, so beware of that. Now let's ask ourselves, why does relative risk aversion appear here as opposed to absolute risk aversion? Well, it's because risky returns are multiplying wealth. Okay, and everything here is proportional to wealth. Okay, so finally, let's grit our teeth and derive that utility function approximation. Again, I can do that because we're sitting here online. Recall that the investor maximizes this expected utility function, and recall the Taylor approximation for a function. So let's apply this Taylor approximation to the objective function. The expected utility of wealth times 1 plus RC is approximately what? Well, the expected utility of wealth when RC is 0, that's just initial wealth, plus marginal utility of wealth at that point W times the first derivative, which is RCW, plus 1/2 the second derivative of the utility function times the squared deviation, RC squared W squared. All right. So these are deviations of wealth from the reference point, which is W. Here's the first order deviation. Here's the second order squared deviation. All right. Now, we're taking expectations of this whole thing. All right. So U of W is known. So its expectation is just itself. The expectation of U prime W RCW, the only thing that's random is RC. So we just take the mean of RC. This stuff is known. And then we have plus 1/2 second derivative times the square of wealth times the expectation of the squared RC. What's that? It's the expectation of the square is the square of the expectation plus the variance. That's true by the definition of variance. So if we take this objective function, subtract U of W, which just doesn't affect the answer, and divide by marginal utility times wealth, again, that's just rescaling the problem, then we can equivalently think of the investor as maximizing R bar C plus 1/2 second second derivative divided by first derivative divided by wealth times R bar C squared plus sigma squared C. Now, over short time intervals, we have that R bar C squared is negligible with respect to sigma squared C. Why? Well, I'm going to wave my hands a little bit at this point, but if returns in each short period of time are independent and you cut the measurement interval in half, both the mean return and the variance of return are cut in half. Well, that means that the variance is halved, but the squared mean return is divided by 4. So as you keep shortening the time interval, the squared mean return becomes negligible relative to the variance. Now, I should mention that this trick of working with short time intervals is a very powerful one. If we take it to the limit, we get continuous time finance, and that lies beyond the scope of this course. But in any case, if we use this observation to simplify equation 7, we'll get equation 6. Let me take you back for a moment. We're going to basically neglect R bar C squared. So we've just got sigma squared C. So if we recall that relative risk aversion is minus second derivative times wealth divided by first derivative. Then that's going to give us this. The investor is actually maximizing mean minus 1/2 relative risk aversion times variance. And that's the result that we can use to talk about portfolio choice. So thank you very much. See you in class.